our last speaker, some short story. This is a company in United States. It's a kind of miracle. Its valuation $8 billion, and no one tried product, but $8 billion. And today we have a director of machine learning of this company, and he will have 1 hour to, I think he cannot talk a lot about Magic Leap, but he will share some more information. And Andrew worked before in Google, so he has a very interesting experience. And also, he's a DJ. But it's not a topic for today, but maybe for tomorrow. And I want to introduce you to Andrew, and make applause. He came from United States. And you have 1 hour. Feel free to speak.
Thanks for inviting me, Vit. It's a great pleasure to speak in front of you guys. As Vit mentioned, I used to be at Google before I got bored, and then I went off to build some stuff at Magic Leap, where we work on mixed reality. It's a bit different than virtual reality and even different than augmented reality. Having said that, Magic Leap is considered the most secretive startup in the world, or ever since the existence of sort of startups in general. So I won't tell you too much about Magic Leap, but I will tell you about sort of the history of neural networks, AI, deep learning, why it didn't work forever, and why does it work all of a sudden, and what are the sort of future directions to take, and how to think about computer vision from the perspective of deep networks and machine learning and learned paradigms in general. So if you look at this sort of timeline, people started thinking about sort of artificial networks, artificial networks and simulating brains almost 70 years ago. Or it started with very simple models in the 40s. Then in the 50s came this notion of a perceptron that's sort of the building block of today's modern neural networks. Then it got sort of updated over some time. Then in the 70s, a critical point happened where the XOR problem was solved. I'm sure you all know about it. And then as sort of things moved on, this sort of multi-layer perceptron came about, sort of this classical neural network model. Then an SVM by Vapnik was introduced. And things kind of moved along, and things worked and they didn't. And for the longest time, we could write sort of beautiful equations and come up with awesome models. But in practice, none of this stuff worked. You could try something in the lab and you could get some cute result, publish an awesome paper, win a prize. When you put it sort of in the real world, it would always fail. So then something dramatic happened in 2012, where Jeff Hinton and two of his students published a paper, as now known, the AlexNet, that kind of showed these tremendous results that really have changed the world. So if I continue this timeline, and I'm going to sort of guess and predict what's going to happen, I think this is going to occur. I think in about 3 years, computer vision is going to be solved. And I'm being pretty serious about this. So I'll go through this talk in a manner where I'll sort of build up the intuition of why these things work, first explaining why they didn't work and what has changed over time. Then I will very quickly present some results of how things work today, and then I'll tell you about some future directions and what I think we should focus on moving forward. So, as a historical sort of background, first there was this perceptron by Frank Rosenblatt in the 50s. It's a very simple model of a neuron. Following that was this Adelane model that's very similar, but except to sort of update the weights rather than the class predictions. People started using the actual activation functions rather than class assignments. So that improved things a little bit. Then as time went on, in the 80s, we start seeing some math that we use today, this back propagation magic. It's fairly simple, but this is when it started appearing. And then deep learning kind of started becoming more of a sort of practical consideration as opposed to just some fad, where people could actually train networks that were more than 2-3 layers deep, but things weren't quite working yet. So you could work out some results on simple examples like MNIST, but in practice for bigger problems it still didn't work. Then really strong results started coming out about 5 years ago, where Alex, Ilya, and Jeff published this ImageNet result, where they completely destroyed all of the classical computer vision object recognition results, and then the world really took notice. So at that time I was at Google working on various object recognition platforms, and once we saw this, every single person completely changed into this deep learning paradigm, and we never sort of looked back, and the results continue to impress us even today. So if you look at this sort of machine intelligence spectrum, this is where we were up until 5 years ago, where humans really teach the computer what it is that they want. They engineer features, they recognize patterns, and they really try to induce intuition and sort of experience into what they've observed over time, into some mathematical formulations that the machines can sort of scale up much better than humans. Where we want to be is here, where machines just look at a problem and they figure out how to solve it, and the solutions may be way beyond what humans can do, but given the computational capacity, memory, and so forth of machines, they should really be able to do this given unlimited amount of data in the real world. In practice, we're somewhere here now, where we have these deep networks, supervised learning, things kind of work really well compared to what they were 5 years ago, but we're still not where we want to be. And sort of, like I said, by 2020, I think we're going to be in this CV complete state where all computer vision problems could be reduced to some solved ones, and computer vision will essentially be solved. So as I mentioned, this is the outline of the talk. First I'll talk about classical neural networks that didn't work, then I'll talk about convolutional neural networks that changed the world, and then I'll describe what's available today and where we're going to move on to tomorrow. So let's start out with a simple setup of a supervised learning problem. We have some inputs X, some labels Y, for some training set that contains P examples. F is some function that transforms the input into the output. When you go into the sort of different examples of machine learning problems, you can roughly break them down into 3 categories of classification, regression, and structured prediction. Now, if you want to take sort of this formulation and apply it to deep methods, nothing really changes except that you're saying instead of just having one single transform between the input and the output, you're going to have a bunch of different ones that follow each other, and you can stack them up to n of them, as many as you need to sort of get the capacity required to solve the complexity of the problem that you have. So in neural networks, let's make some assumptions for the next few slides. The image is a vector. The class of functions, these F1 through Fm that we should consider, are just simple functions that we compose together. Now, one sort of natural question that comes up, if these functions F1 through Fn are simple and perhaps linear, why can't we just linearly combine them together? And if we do, what happens? And I'll answer that question in a few slides. So to start thinking about these things in a sort of more realistic way, let's look at some biological intuition behind why this makes any sense. So if you look at a sort of this graphic representation of the cell of a neuron, in fact, you have some dendrites, some signal that comes into the cell body. Then something happens, and then the axon carries out the output of the input that's been aggregated into in the cell body of a neuron. If you represent it sort of in a simple mathematical model, it looks like this, where you have a bunch of activations coming in. They're all weighted by some weights learned, or as previously was done, preset by a human. Then there's some aggregation of these weights with some bias, and then this summation undergoes some transformation through an activation function, and that becomes the output of that axon, and then you can feed it into the next neuron, and you can do this sort of indefinitely. So if you take this formulation of a model of a neuron and you compare it to the perceptron, you realize that it's in fact almost identical. You have some inputs that are weighted by some weights. There's summed over in the sort of the cell body or a hidden unit, and then they go through an activation function, in this case a step function, and then you get the output. So let's consider an example of a simple neural network that uses this sort of formulation. So this is a 2-layer neural network with 4 total layers and two hidden states. So you have inputs, you have hidden units 1, 2 layers, and then the outputs. So you go from an input through this first perceptron model. You get some hidden unit activations. You go through the second one. You get some more hidden unit activations, and then you finally get the output. Now, some definitions, unless everybody already knows this. So there's this process of forward propagation that basically means that you take an input, you pass it through a network, and you get an output. That's considered a forward propagation. So in this particular case, to compute H1, we basically pass input X weighted by some weight matrix and adjusted by a bias, compare it to 0, and take the max of this expression. And this max is so-called a nonlinearity, and there could be many of them, which I'll describe in a little bit. And then you basically continue this process forward until you get to the output. So why do you need these nonlinearities? And this is a question that I formulated a few slides ago. And the main reason is that if you don't have a nonlinearity between these layers, then all of your activations essentially collapse to a single logistic regression function, and you don't have this sort of deep representation. Furthermore, when you have this max operation, or as we call it, rectified linear unit, you're able to represent highly non-linear manifolds by piecewise linear tilings. So things are piecewise linear in a very, very local neighborhoods, but when you stack them together in a deep network, then you're able to represent very nonlinear manifolds. As far as activation functions go, there's a large number of them. Originally, people were using a sigmoid function, which is a sort of a simple logistic function that's sort of also biologically motivated, similar to the hyperbolic tangent. But it turns out that this ReLU, leaky ReLU, and ELU are the sort of the simpler functions that we use today, because they make sort of learning and training much simpler, and I'll get into the details of that in a little bit. Now some practical considerations. Why do we need many layers? This is a very sort of tricky question, because most people would just answer, because without them it doesn't work, and if you add more layers, then it just works. The reality is there is some explanation to it, and the explanation is that you want to create a representation that's hierarchical in nature. So you want parts of the network to represent simpler features in the image that are learned. Then higher up in the network, you want to represent object parts, and further up, you want to represent the entire object. So in this example, you have a truck feature that's however many dimensional, may be binary or in floating point, doesn't matter. But you see that these activations represent individual parts of the car itself. So this is the radiator, these are the lights, and this is the wheel. And the goal is that as you train these networks, these sort of intermediate representations will not belong just to one class, but will actually be shared across multiple classes of objects that you're trying to learn. For example, if you have this truck feature versus a motorcycle feature, you see that the wheels actually correspond to the same representation. And that's why you're able to actually efficiently learn, because the representations are shared and they are hierarchical. As you look at the activations throughout the network, in the first few lower convolutional layers, you see activations that resemble Gabor functions, or these filter banks that were very popular in the 90s. Then in the mid layers, you see object parts, like wheels, fenders, and other parts of objects. And then finally, at high levels, you actually see the individual objects, and you're able to detect and localize them in images. So the hidden units that are present in the network, they could be thought of as feature descriptors or classifiers, which is effectively the same thing, just one being discriminative and the other is not. Again, the question of layers and how big and wide these networks need to be, it all depends on the complexity of the problem and how much data you have to sort of feed the network. There's been a recent theoretical result that shows that you can approximate any mathematical function with only a two-layer network, modulo that you're allowed to vary the size of each of those layers. The weights of these hidden layer matrices are originally set at random, and then they're learned throughout an iterative learning process using stochastic gradient descent. Now, so how do you know if your network is actually learning or doing anything useful? So you have a network itself, and you have some truth. So remember, this is a supervised learning problem, so you have some answer to an input that you have. So you have this XY pair. And in fact, a very simple sort of metric for evaluating how good you're doing is to use a softmax function, which is just another version of logistic regression. So then the loss of this computation just becomes a negative log likelihood across the inputs and the outputs, and this works quite well if the number of classes is not too large. In practice, you can go to about 15 or 20,000 classes before it starts to break down. So during training, you essentially want to minimize this loss, given a bunch of input samples, their ground truth or their labels, and then some parameters theta of the network. So you want to find an optimal set of parameters such that this quantity is minimized. So in order to do this, you use this magical algorithm called backpropagation that was invented by Jeff Hinton in 1986. And now we'll go through it, and I'll show you exactly how it works. So first of all, you want to be able to differentiate all of the components of the network, and you want to start out with this loss. So you have a softmax, you have your loss. If you substitute this first equation into the second one, and you take derivative with respect to theta, then you get something like this, which effectively tells you what is the difference between the probability of x given its assigned class and the actual truth. So it's very straightforward to interpret. So when you're doing backpropagation, you start out at the loss, and you start to take derivatives first of the loss, then of the sort of the second hidden layer, then the first hidden layer, and so on. And you keep taking derivatives, partial derivatives, with respect to these quantities, given all the parameters of the network. So for instance, in the first case, you take the derivative of the loss with respect to the weights in the last hidden layer, and you take the derivative with respect to the actual activations. These are the derivatives, and then the rule that tells you which way to change your weights and your activations is this. It's basically a difference between what you had and what the gradient tells you. So very simple gradient descent updates, partial derivatives with respect to every single component of your network. And then you just continue doing it the same way until you reach the beginning. And you just keep iterating until the network converges. So this backpropagation and forward propagation are effectively inverses of each other, where in one case you accumulate information from the beginning of the input until the very end. Then in the backprop case, you actually try to decompose things back from a single output to a multinomial input. Now, unfortunately, none of this stuff really worked. But the mystery is that between it not working and it working, very, very little changed. So we still use the same backpropagation algorithm, we still use the same gradient descent, the same activation functions, but something has changed for this magic to appear. And in particular, we want to go from this multi-layer perceptron to this ridiculously large deep neural network. This particular station is called a ResNet that has 152 layers in the network that trains quite well. So what's the magic and why does it work? So the answer is this letter C, which stands for convolution. And without these convolutions, things didn't work. But with them, all of a sudden, things start to make sense. So now the question is why? So if we look back into sort of neuroscience from the 50s and 60s, we remember this experiment that Huber and Wiesel did with a cat, where they started showing it oriented lines and edges and tried to measure responses in the brain of a cat. And they found out that if you just look at individual samples, then you don't get a response. But if you aggregate these 3 points in a line, then all of a sudden the neuron starts firing. So that gives us the intuition that if we look at things in isolation, and originally I said that the inputs to the networks are just these strung out vectors. So even if it's an image, we destroy all the spatial information, we turn it into a one-dimensional vector, and we push that through the network. So that turns out why things break. If you actually keep the spatial information intact, it turns out that that's what activates sort of recognition and perception. So the first example of this was this neocognitron, this deep learning model in the 80s that tried this idea, but it was never really pushed far enough, so it kind of died, and it was only revamped by Jan LeCun in sort of mid-80s, where he used it to build Linnet. So these convolutional neural networks, they have this very interesting property that even though the network can be extremely large and dense and so forth, it consists of this sort of conceptual block. And the block does the following. It does convolutions, then it does some kind of a normalization and nonlinearity to the output, and then it does some pooling. So you take an image, you apply some learned convolutions, you get some response, you normalize it, then you pool, and then you proceed. If you notice, this is exactly the same thing that all these engineered features do. Hog, sift, sort of these binary features, whatever your favorite old sort of method was, except that all of the constructs of these features are not engineered by hand, but they're actually learned from data. And that's the difference between things working and not working. Finally, when you have all this component intact, you basically stack them all together, maybe add some more capacity if your network requires so, and that's your general network. In the second half of the talk, I'm going to argue that you can actually build any deep learning system just using these components alone and nothing else. So now let's look at some of these modern architectures. This is an architecture from Jan LeCun from 1998 that's been used to recognize the written digits. This is a network that was sort of revolutionizing things by Alex and Jeff Hinton, AlexNet. This is a model that I built at Google called GoogleNet, or the Inception model. It's super complicated, unnecessarily so. And now this is like the largest, craziest beast. It's called ResNet, that has 152 layers in the network. So what really changed between the classical to the convolutional models is that the convolutional layers is what gave us the opportunity to do this Huber-Wesel solution, where you actually put nearby signals together, forming more complex structures, and those are the things that you're actually able to learn. Because if you look at some very simple sort of inputs, then there's not enough signal to interpret what's going on. And that's the main difference between things that didn't work and things that did. There are a couple of sort of other tricks that were invented along the way, but those aren't really critical to the success of the story. So let's look at these individual components, because I mentioned that these are all that you need to know to really build deep networks. So let's look at the individual pieces and see what's going on. So the convolution takes this sort of inspiration from this neuroscience experiment, where you're saying, I want to take all observations, say all pixels, and connect them to one hidden unit, so the system really knows about the spatial construct of the entire input. Unfortunately, this doesn't work really well because the number of parameters becomes too large. Most of the things in this part of the image versus the center of Einstein's face are not really related, so it's not that important. And finally, you will never have enough data to fit a 2 billion parameter model. Now let's go to the next logical thing and simplify this and say, well, let's just have some locally connected components, one in this area, one in this area, one at the bottom, and so forth. So that's okay. It would work, but it would only make sense if you always assume that the structure of the image is the same. For example, if you're doing face detection and you've aligned, or face recognition rather, and you've aligned the face perfectly in some canonical coordinate system, and you know that the left eye is going to be in one part of the image and the right part in the other, and it's always the same. Then these learned features would always fire in the same parts of the face, and it would work fine. But unfortunately, in the real world, the images are not aligned, so this would not make sense. Now, what if we go beyond this and say that we will construct these convolutional filters and actually push them across the whole image in such a way that if this pattern repeats itself, for example, in this part of the image, then you would use the same activation or the same filter, and then, but if it doesn't, then you would learn a new filter. So that way, you will only learn the components, or the dimensionality of your learning problem will only increase with the complexity of the input rather than with the definition of your model itself. So the convolution works effectively like this. You slide it across the image and you fill the output. And if you see, the input originally is 6 by 6, and the output is 4 by 4. So the border pixels disappear due to this padding property. So after you run a convolution, for example, now you've learned this filter, and this filter is just essentially a line detector. So it'll tell you that or rather an edge detector that it tells you that in this particular place the image goes from dark to light, and this is what the network learns. So once you apply this filter to an image, you get this output. Of course, you can design this by hand, but when you go to real and more complex problems, these filters become highly non-trivial, and designing them by hand effectively becomes impossible. So how does this actually work in a network? So remember, we have this output feature map H that takes the previous input, whether it's the actual input or the activation from a previous hidden layer. You multiply it by learned weight, and then you pass it through a nonlinearity. So these are the previous feature maps, these are the new feature maps, and they go through this convolutional layer and through this nonlinearity. So the math is sort of fairly straightforward, because you just start out with adding up these pixels that go to this location, then you do it for the next one, and so forth. So this is just basically a linear weighted sum from all inputs into the output, and then it's multiplied by the filter that you've learned. The backpropagation case is effectively as easy. You basically have to go from the output y to the inputs x, and then there's just a very straightforward sort of calculus to push through this. So when the convolution is performed, there's an effect, as I mentioned earlier, due to this padding issue and the size of the filters, the inputs and the outputs change in size. So in order to, if the goal is to retain the size of the image in your feature maps as you go through the network, there's some care to be taken with padding, but essentially the sizes of inputs and outputs are sort of easily computed, and they're deterministic. Now there's a question, how many of these convolutional filters do you want to have? And that's another sort of this empirical result that you come up with once you have a particular problem that you want to solve. But in general, the number of filters is proportional to the dimensionality of the problem. If the problem is very simple and you want to recognize two classes of faces, then the number of images, the number of filters doesn't need to be that large. But if you want to solve a very large 1,000-way classification problem, then of course you need more dimensionality to control the learnability of the task. Now the next block is this batch normalization and nonlinearity. First, let's talk about this batch normalization. And all that says is that once you get an output from a convolution, you want to make sure that your features that you get out of it, they're basically normalized to zero mean and unit variance. This is very simple and just allows you to learn faster, because if the distribution is of super high difference in scale, then it will take forever basically to learn from examples that are of high magnitude versus the low ones. Again, every sort of operation in a deep network needs to be differentiable. So this is also fairly simple to differentiate. With a simple chain rule, you get these updates, and it works quite nicely. Now this next step is the nonlinearity. So we first start out with this logistic function, the sigmoid, and this is sort of biologically inspired, where it's a smooth step function, and you can vary its curvature and the slope. Now the problem with this thing is that if your weights or activations are outside of this slope and are close to flat regions, then if you take derivatives of this, then of course the output will be zero. So you want to avoid these regions to avoid this problem of vanishing gradients. Basically, if you get an activation in these flat regions, then you don't get any response and you can't learn. So people propose this alternative formulation called the softmax, where you basically chop this thing off and let the function go to infinity, and This solved a lot of problems and it made things okay. But then came another constraint saying that our networks are extremely large and redundant, and in order to make them learn more efficiently, we want them to, the activations or the representations to be sparse. So how do you sparsify this function? You basically dumb it down like this. And this is called a rectified linear unit. And what happens is that whenever the activation is negative, you make it 0, and whenever activation is positive, you just leave it alone, and that's it. So how do you can you do sort of backprop through it? And that's also very simple. In the forward pass, you just take a max between 0 and the actual activation, whichever one goes. And in the backward pass, if the activation is negative, then it becomes 0. Otherwise, it just stays as it was in the previous layer. Very straightforward. And finally, this pooling operation, and what this allows you to do is to retain sort of translation invariance. So when you have an image, it doesn't matter whether the face is in this area or in this area of the image, so regardless of where the object is, you achieve this translation invariance. So all that the pooling layer does is from layer to layer, it says, I'm going to take a neighborhood, in this case, a 2x2 window, and I'm going to pick a max out of this neighborhood, and that's what I'm going to represent the activation map in the next layer, therefore aggregating information spatially. There are multiple ways to, so this is the forward pass, how you push in the network when you're training forward, and then when you train backwards, when you compute the backprop, there's a number of different methods of solving it. The most efficient one is when you go from 1 pixel back to 4, you have to choose which location attributed to the maximum. And the simplest thing to do is just pick one at random and say, it's okay, it'll just work. Surprisingly, it kind of works. If you give enough examples, it learns to statistically find a way to find the right activations. The next best approach is to take the activation and to just distribute it such that the sum of all the activations in this bigger window sum up to this one. That doesn't work as well. That's not a good idea. Finally, what works the best is if you actually keep track of where the maximum activation from the bigger window came from, and you just write it down in some lookup table, doesn't take much space, and when you do the backprop, you say, I know that this value came from this location in the array, so that's where I'm going to put it, and the rest I can just zero out, and that doesn't really matter that much. So there's, again, like with all the other layers, there's a number of decisions you have to make about the size of these pooling layers, how many of them to have, and the answer, again, is sort of it comes with practice, but the gist of it is that you don't want to pool too much because you average too much, and the smallest amount of pooling is 2x2, and if you do it consecutively enough times, you will sort of add up to the entire size of the image, so that's the best way forward. So when you train these networks, you basically do this forward propagation where you compute the activations moving forward, and then you do back propagation, then through gradient descent you do gradient updates, and then you basically learn, and then as you learn you watch sort of a number of different visualizations, and you understand how your network is performing, and if things are sort of working, it converges. If not, then there are a bunch of problems. So this is the training time, and at test time, again, you have these weights for the filters of the convolution, for the hidden units that you've learned. So when an input comes in, you essentially multiply an image by a bunch of these matrices, and at the end you get some, you pass it through an activation function and you get some output. And that effectively is how this works. So even though at training time it may take a very long time to learn these numbers, at test time this is extremely, extremely fast and can be done sort of at super high frame rates, which is sort of classical computer vision could never achieve this result. That's why we never had sort of commodity models. So then it sounds all good, but what if it doesn't work? Like, what do you do if your model doesn't train? There's a number, sort of all of these things are useful to know and understand, but deep learning frameworks have evolved so much so that all of this sort of, if the backprop is incorrect, if your sort of gradients vanish and so forth, all of these attributes of learning have actually been integrated with the new deep learning frameworks, and you don't really have to worry about this too much. The higher level concepts you still have to do by hand, whether you have to figure, for example, you train a model on some data and you get 100% accuracy, and then you go into the real world and it doesn't work. Then you have this generalization problem where you do well on training data that you probably overfit to, and then you go to the real world and it doesn't work. So basically the transfer learning doesn't apply. The distribution that you trained on does not match the distribution that you test on, and your network collapses. So these are still the kinds of things that you have to worry about and think very sort of hard about, because this is the problems that are still not solved, and this is something I'll talk in the rest of the talk. So now let's focus for literally a few minutes on what's available today, and then I'll go on to talk about what sort of the frontiers are and what the problems that I concerned myself with these days. So I'll show just a few examples of the tasks that I consider extremely hard in computer vision that are actually solved today, and then we'll move on further. So today, you've all seen this, right? In the movies, they show, this is the face. We apply some Voronoi diagram, and all of a sudden, we find the guy's face. Magic Terminator stuff. Of course, it doesn't work like this, but it turns out that it actually works now. Face recognition is a completely solved problem to 100%. There are papers from 2015 and 2016 that show that this is really a solved problem. Given enough data, it's impossible to break. In Baidu, for example, all sort of entrances to all the buildings is done through face recognition like this. There's no more keys or anything like that. And this is done using this notion of a deep metric learning, something that I haven't talked about, but I'll be happy to discuss offline. The next problem is semantic instance segmentation, something that I sort of wrote my PhD thesis on. And this is an example from a paper called Objects in Context from 2007, where I tried to illustrate a point that context is extremely useful, because if you see a yellow blob in the image and a tennis racket and a person, then it's likelier that the yellow blob is a tennis ball and not a lemon. This picture was sort of a schematic of how context helps. This was in 2007. This is today. Sort of, I never thought that within 8-9 years would be able to get this good of accuracy, but now you see this sort of per pixel classification works extremely well. It works, and you can run this in real time, and this is called Mask RCNN network from my colleagues at Facebook. And then finally, a very cool new result that comes from CMU that has to do with human pose estimation. And if you extrapolate this problem onto many other things, you can see how by solving this, you can actually solve very many articulated problems in computer vision. And these results are quite impressive. So think of, these are just some models that are sort of computer generated, but then as time goes on, you see that this is actually real people whose skeletons are being detected in real time. There's absolutely no tracking here. It's frame-to-frame pose estimation, and it works for multiple people. Again, it runs in real time, so this is a very impressive result. So now let's sort of shift gears moving forward as to, now that we have all these things working, what should we be doing next? So these are some of the advanced and active topics in deep learning, something that both my group and sort of other leading groups in deep learning concentrate on. They involve regularization, something that allows you to sort of not overfit. Domain adaptation, where you learn on one task, but then you perform your inference on another task. Same thing that goes for transfer learning. There's a new class of generative models that sort of is an example of unsupervised learning. There's multitask learning, then a number of sort of optimization techniques. And finally, there's this notion of structure learning, because currently we've sort of moved away from engineering features but learning them, but we now instead engineer networks, which is not the best of a solution. So there's a number of new works that are coming out where people write algorithms that actually generate neural network architectures from data, as opposed to doing it by hand. But today I want to tell you a little bit more about multitask learning, because it sort of explicitly relates to my work, but that's probably as much as I'll tell you about Magic Leap at this point. So think of it this way. Think about all of these problems, and let's assume this is all of computer vision. I'm sure there's a bunch of other tasks that I'm not mentioned here, but for the sake of a discussion, let's just assume that this is all of computer vision that we have to worry about. And let's suppose that each of these problems are actually solvable today in isolation. So for a sort of new modality of VR or drones or self-driving cars, you actually have to solve them all in order to build a system that works, right? You can't just say, I can detect people, but I can't track them, so it just wouldn't make a complete system. But then if you solve all of these problems in isolation, it's very difficult to sort of make it a practical use case, because each single one of them would take a very long time to compute, and it would require a lot of resources. So, like I said, the first assumption, or the first sort of go at this, we say, let's come up with a deep neural network that solves each individual tasks. And this we can do today. We can find results using deep networks that solve each of these tasks to some level of accuracy. Now, is this feasible? Unfortunately, it's not, because it's hard to scale. As you add more problems, the capacity and compute increase also linearly, which is not good. It's very expensive to train, because you need a bunch of redundant data sets that are not connected. There's absolutely no regularization, because if you solve one task, it doesn't tell you anything about the solution for the other one. It doesn't generalize, because the tasks are completely separate. And finally, there's no feature sharing. If I learn from a very large data set for classification, and I have a tiny data set for head pose tracking, then I can't relate the findings from one example to the next. So that's an unfavorable situation. The next best idea is to come up with these meta tasks. So as commonly done today, let people say, let's combine detection and segmentation into one, and let's combine maybe visual search and face recognition, because they both sort of worry about detecting objects, and you can think of a face as just another object. Then in classical SLAM systems, tracking and estimating depth goes hand in hand, because you estimate pose from one frame to the next, and you can learn depth in a similar fashion with those setups. And then finally, this illumination mapping kind of stands by itself, because it's more of a graphics thing that's not related to other things. Does this solve the problem? Even if you combine them into single models, the problems still remain. It's still hard to scale. It's still linear and increased capacity in the big O sort of notation. But the biggest problem is that where do you get these meta tasks? There's no oracle that tells you which problems in computer vision should be solved together and which ones should be solved separately. So it makes it very difficult to do. Or again, you can sort of engineer it by hand, but the likelihood you won't get an optimal solution. So the alternative is to do something like this. Regardless of whatever inputs you have to your model, whether it's images, whether it's GPS coordinates, LiDAR, it doesn't really matter. And regardless what problems you want to solve at the very end, you build a single deep net that solves all of it at once. That way, you can do all of the tasks, the things that I said didn't work previously, but now they do. All the feature sharing is present because all the features are common across all the tasks. There's transfer learning because you can train on a bunch of different data sets for the same model, and so forth. So as you go down the list, you see how all of these things start to make sense. So I've given you sort of this paradigm, and you're sitting there probably thinking, this guy is crazy, how could this ever work, and why would it even work? So the answer to this comes, I've actually given you the answer already, and this is from the fact that all of these functional blocks are the same. For all of these tasks that we're solving independently, they're all solved with these sort of three functions. And I could argue that if I give the function sort of unlimited capacity, I can have as many convolutions, I can create as many deep layers as possible, and maybe I can even unroll it in time, like this. Then I can solve any problem, because we know that a two-layer neural network with expanded capacity can approximate any mathematical function, and surely there is a mathematical function that solves vision, we just don't know what it is. So let's start from the top. So the main reason is that all these blocks are the same. Then now let's see if this actually works from this previous list of what's good and what's bad. So first is this notion of feature sharing. Think of it this way. So there's this model called SegNet that does semantic segmentation of images, where you're essentially trying to classify each pixel into a number of classes in some data set of 50 or 100 different categories. And these are the filters that are learned in the first convolutional layer for that particular problem. Now you take another problem, the ImageNet, that's solving not a per pixel classification problem, but a per image classification problem, and not over 100 classes, but over 1,000 classes. And if you look at also the first convolutional layer activations, you see that these things are actually the same. And then, so effectively, no matter what problem you're solving, if you're given enough data, the first convolutional layers of any model learns the same stuff. It turns out that it works the same way for people. If you take two people who, one lives in Africa and the other one lives in Odessa, and you look at their complex cell activations, you see that they actually respond to the same stuff, even though one may never have seen palm trees and the other one has never seen snow. Then we go to transfer learning, which is the next item in our desired list, is of transfer learning. For example, in this SegNet model, I want to train a network, but I don't have a lot of data. But for this ImageNet model, I have a ton of data, and I train the network to predict per image classes, and I do very well. So what I can do is I can take pre-trained layers, individual layers, from one network that is of different structure than the one that I want, and simply put them into the other network and continue training, or as we call it, fine-tuning, and it works extremely well. So I can take all the knowledge that I've extracted from this model and simply push it into the next one, and it creates a paradigm where the learning from few sort of labeled examples possible. Now, with respect to regularization, so assume that this is an input image, and one of my tasks is to learn the normals in that image. And another task is to learn the depth in that image. And finally, the third task is to learn semantic labels per pixel, where this is a bed, this is the floor, and this is a wall. So if you think about it, if you're trying to segment an image by the label, and you're trying to see if this pink area is a floor or not, the fact that all the normals in this area point in the same direction is a huge boost in telling you whether this should be a floor or not, right? If you know where gravity is, and it tells you that all the normals point against gravity, chances are it's not a wall. because in the case of a wall, it goes the other way. So because of that, you get these generalizations that allow you to create a manifold where in this figure 1, the example is as you move in this basin and change the parameters of a network, the minima doesn't change. You're still in a global minima. But if you do it without this generalization of solving multiple tasks at once, you get this very peaky manifold where small variations across X or Y or other million dimensions that the network has would quickly push you out of the local minima and lead to a degenerate solution. So putting it all together, you get this network that has this set of convolutional layers that are shared across all tasks. We call it a trunk. And then you have these smaller, much smaller pathways, T1 through Tn, that correspond to one specific task that you're doing. One for segmentation, one for detection, and so forth. Finally, all of these pathways merge into a single loss. There's just a summation, a weighted summation across all the losses, plus a regularization term of this trunk. And then you train this thing jointly. And at the end of the day, you get answers for all of the questions that you're asking within a single model, given all the benefits that I described. Now, in terms of training, all of these pathways have different labels and have different properties of the data that they want to describe. So different data sets have to be treated a little bit differently. So to train it, this trunk or this joint shared set of convolutions is trained with the biggest possible data set that you can find. In this case, ImageNet is such a data set that consists of about 10 million images to date. And then the individual pathways, they're all trained with their respective data. Whichever data set has the depth is trained with depth, whichever has the segmentation is trained with segmentation, and so forth. And so all of the models are pre-trained individually like that. Then when you combine them into a single model, the bottom layers, or the shared trunk, is fine-tuned on all the data sets. So all the data goes through this trunk, and you make sure that the activations of the lower layers actually are represented for all tasks. And then the specific pathways are only, again as before, are only trained on specific task data. In order to make it work, you have to be very careful to make sure that imagine here that T1 has 10 million examples that you can train from, and this is for segmentation. And T2, which supposedly is face recognition, only has 10 examples. So your network will very quickly learn how to segment really well, but it will never work super well for face recognition, just because it doesn't have enough attention and there's not enough foundation for it to do so. So when you apply these normalizations, you have to apply these notions of rolling batches, where you keep track of the number of examples given to a given task, because if you don't do so, the network will just overfit to a specific pathway. Now let's look at some actual results of this multitask learning in its early days and see what's going on. So this first table that I'll describe is from my colleague Andrea Vidaldi, where he tried a classification task across 10 different data sets. One is this CFAR10 of really tiny images, one of this classical MNIST, and one is these house numbers from Google. So originally you trained 3 separate networks. This is what no sharing means. You get 9% there for this one, 0.3% there for the MNIST, and 3.7% for the house numbers. Then if you go to full sharing, where you create a single model that solves them all, you see that the difference is really minimal. And the model learns to classify things essentially just as well. So then you might say, well, it's sort of the same task. You're just doing classification on 3 data sets. There's not much difference, so it's not surprising that it works. So then let's move on to a slightly more complicated problem. This is some of the work that we did at Magic Leap, where we're trying to, from a single view of a web camera, we're trying to understand the layout of the room, basically find all the surfaces and their junctions. So if you simply train a model by finding key points, and key points correspond to junctions of planes in the room, then you get this 6% error. And then if you add another task of finding these key points and also classifying the room type as to you're looking at a corner, or you're looking at a straight wall, or you're looking at a ceiling, and so forth. So one is effectively a detection problem, and the other one is classification. Then you see that the detection accuracy doesn't drop while adding a classification pathway such that you're allowed to solve both problems at the same time. Then you expand to this model called UberNet that's trying to solve detection, classification, pose, and a bunch of different things. There's a total of 7 tasks. I really encourage you to read this paper. I think it's an oral at CVPR this year. So again, they go from, for the detection task, when they give a few state-of-the-art results using some other methods, you get sort of results in the 70s. Then they replicate a single detection task with their model just to make sure that the model performs adequately with respect to all the other competitors. And then they start adding more tasks. So in the task 2, they added segmentation to detection. The results actually improved because of all these generalization properties that I mentioned. And then when you go back to 7, there may or may not be enough data, so the performance slightly drops, but it stays within sort of the margin of standard deviation, so it's statistically, the error is statistically irrelevant. Now they do the exact same thing for the other task of semantic segmentation. They also compare to sort of state-of-the-art methods. Their single task model performs on par. When they add the second task, it still sort of performs on par. And finally, when they add all 7 tasks, it degrades a little bit, so it should work better than it does. But this is attributed to the lack of basically training data. So if you train it a little bit more, it'll get back up. Now, in terms of originally, we started saying that if you have all these sort of tasks that you want to solve, it becomes very difficult, because if you solve them individually, you basically run out of compute power and you don't know what to do. So now if we combine it all together and we look at the computation, there's in deep networks, there's really 4 types of sort of computations that are required. You have to compute sort of the number of output values that your network produces, the number of values that you read from memory, the number of times you write to memory, and the number of times you compare, so you can actually compute your gradients. As you see, when you start, so this is the network that we're looking at, and it's sort of, if you turn it sideways and you put it along the x-axis, these are the layers from the very beginning until the very end. So as you see, all of these 4 compute sort of paradigms map extremely well onto this plot, where as you go deeper and deeper into the network, the amount of computation you have to do reduces exponentially. So what this tells you is that if you have this trunk of shared convolutions that I showed you earlier, if you share those up to, say, layer 3 or layer 4, then at the end you can add as many of these additional pathways as you want, and the computation of the network will never increase beyond sort of a log scale. So you can add 10 pathways or 20 or 100, they will never get bigger than the original trunk computation, and you'll be fine. Another way sort of looking at this is that by the time you get to the second or the third convolutional layer, you've already done 75% of all the computation you need to do in the network. So by the time you get to the top, these things are so insignificant in terms of compute that you can add as many pathways as you want, because all of the work has already been done at the bottom of the network. So I think I'm running out of time, so I'll start to wrap it up. So in conclusion, deep sort of supervised learning is the most practical and successful approach to machine learning today, and that of course includes computer vision. These convnets have really become a commodity today, so there's really no reason for anyone not to use it, because it's really very simple and you can get going with it sort of in a matter of weeks. In terms of scaling it, there's three important components. One of them is just increasing compute. Instead of training on one GPU, you get access to some AWS cluster and you train on multiple machines. Second, sort of the rules of the game nowadays are such that whoever has the most good data wins, because everyone essentially has the same algorithm. You can try to tweak it to modify absence of good data, but the sort of the realization that I came to is that rather than trying to perfect your network to sort of deal with imperfections in your training data, why not just create unlimited amount of perfectly training data? And to do so, you use synthetic data, and a lot of people sort of across various companies are doing this now. So you synthesize the entire world. By doing so, you get all the labels for free during construction. And then you train your networks to be evaluated on real test data, and then you evaluate the mistakes, and then once you understand what the mistakes are, you go back to your data generator and you say, just create me more of these examples that I messed up on, and then you do this sort of active learning loop until you get good accuracy on your test set. Finally, there's this multitask learning that I talked to you about, which is the only paradigm sort of known to date that allows you to solve multiple tasks at once, and that's what's required for these sort of modern AI tasks of AR, VR, drones, and so forth. Finally, deep nets are extremely redundant by construction. So even when they're very large sort of on paper and they take forever to train, in practice they can be very, very small, and they can run on any kind of embedded devices, phones, ASIC chips, or even sort of out-of-the-box DSP processors. So with that, I'll stop and I'll take some questions. Thank you.
Andrew, thank you for your talk. I want to give you one note. We all understand what Andrew working in a big company, so he cannot share a lot of technical details. But what you can 1000% learn, how you have to talk about what you're doing to have a valuation of $8 billion, okay? This is a value, 1000% of this value. And I'm pretty sure what you can speak at after party, and you can get some interesting insights, technical insights. So we have time for maybe 5 questions. First one.
Thank you for a nice introduction to neural networks. And I have rather a comment than a question. So I'm doing face recognition, and I can tell you for sure that it's unsolved. So currently, state of the art is around 76%. And when you are watching on some numbers like 99%, the only thing it says that this benchmark is too simple. So it's something that you would say, if I can classify MNIST well, it means that I can do optical character recognition as well. So yeah, and so face recognition is unsolved, and interesting point on that is the last results were not from the neural network architectures, but rather on different loss functions. So I think it's an active area of research, and you cannot solve it just taking VGG or like Inception and just train on the bunch of the data. So I wouldn't agree with you that currently it's the deep learning is easy. Also, yeah, like a lot of stuff is doing, and I don't believe that computer vision will be solved in 3 years. Sorry.
That's a perfectly normal sort of view of things. I don't think that deep learning is easy. I think that deep learning has allowed us to solve a lot of problems that we've been trying to solve for a very long time. With regards to face recognition, you have to remember that all of these tasks that we're doing, they're not the sort of theoretical findings that describe sort of laws of nature. These are purely engineering tasks. So when I say that face recognition is solved, I mean that given enough data and given enough compute, you can solve a given face recognition problem. If you don't have enough data and you're trying to sort of learn from few examples, that may be the case.
If you have all the data that Google has right now, you cannot solve it. So it works only in some laboratory conditions, but in the wild, it doesn't work. The labeled faces in the wild data set is not the wild.
Sure, that's true. So the example I was referring to is sort of the security system at Baidu, where I think there's about 60 or 70,000 people that all go in and out of their offices using face recognition.
You have 3D scanners in there?
No. It's a single camera. There's no 3D scanners. 3D scanners don't work outside, right?
They have inside of the building,
yes.
And it has 3D scanner to solve this problem when you're showing a picture, but not the real person. So I'm referring to the current benchmark, MegaFace. So the recent results from some guys from Skolkovo, they just did some, I don't know, some magic, and this magic is around like 80+%. So but still, so like my point is that I wouldn't say that right now we can solve some problems. I think we can solve some benchmarks, and the only thing we can find is that our benchmarks are not too realistic. So, like they're gathered by human and all this stuff. So, just yeah.
Okay, this is exchange of opinions, okay. And you understand this is not American auditory. We have another, two more questions, but...
Hi, I have much more simpler question, not comment. So your talk is this past, present, and future. So it was a very good overview of past, a good overview of done now, this Ubernet and like other works. But for the future, you only mentioned that we will solve everything by 2020. So could you elaborate more on your opinion about future? Thank you.
So this discussion of multitask learning, I think, is an aspect of the future, right? Whether we all agree on whether segmentation and face recognition is solved completely or not, you can at least agree that all of these problems are solved to the point where they could become practical in the real world. However, if you solve them in isolation, that makes it an impractical system. So multitask learning is this direction of the future that doesn't really exist yet. This Ubernet and other examples are just a glimpse of what multitask learning will be. But as I mentioned earlier, I believe that this is a very promising direction moving forward, including things like domain adaptation and structure learning.
You have a question, yeah?
Hi. In any case, thank you for coming, and thank you for sharing your opinion about future of neural networks. But I'd like to point out to some results that should be not validated, but at least I'd like to play with them, and I think a lot of people in this room also. I'd like to talk
just a few words about Ubernet. Yes, they have quite cool results. It's okay, but I've just checked the paper. I've checked the link to their site where they propose in 16 years they will put their network and their architecture, but there no any network, no any architecture, and 502 error bad gate rate. So I'd like just ask if it is your friends, can you ask them put the realization of such network so we may validate this?
So I completely agree with you that it's the reason why, one of the reasons why deep nets make such progress is because people share code and data so openly, and I think I certainly do that and many others as well. I think the reason why Kostas hasn't done it is because he's kind of a one-man show and he's getting ready for this presentation in Hawaii for CVPR, but I'll certainly ping him and ask him to open it up for everyone. Sure.
Okay, one from here and after that, yeah.
About multitask neural network, you put the same loss function for any of these tasks, and
It's not the same, no. It's not the same, no.
But each task has his loss function and different outputs. How can we put it together?
So they all have different outputs, but the loss can be compared across all tasks. And there's a weighting parameter that tells you how much of a weight to give to each loss, right? So at the end of the day, each loss function gives you a value. So you take all these values, you weight sum them together, and that becomes your cumulative loss across all tasks.
So it's possible for existing single loss function for any of these tasks, classification task, localization, clusterization, and other, and we have only single loss function in multitask neural network.
Correct.
Okay.
Okay.
There is no issue about adversarial examples for neural networks.
Sure.
And my question is, have your group done any experiments with adversarial examples with multitask learning? And if yes, what was the results?
No.
Okay, then the next question. Do you think that multitask learning could defeat this problem?
It can, because considering that I haven't done this at this point, it's just a speculation. But the fact that there's generalization across multiple tasks, it's very difficult to come up with these adversarial examples that would kind of cheat all of the parameters. I'll tell you how these adversarial examples came about. When we were building these very large classification models at Google, one of my colleagues found out that if you take an image of a cow and you add a little bit of noise, so perceptually it still looks like a cow, we run it through the network and it gets predicted as a monkey. So then Christian and Ian wrote this paper about adversarial examples, and then in practice, you also see this quite often. For example, if you have fluorescent lights in the room and you take a static picture of an object and you run it and you record it for a few frames and you run it through a network, you see that the flickering in the light actually causes the class changes. But now if you think about doing this in a multitask way, would the labels change not just for the semantic labels, but also for the depth and for the normals and for the lighting and all these other components? So what I'm saying is that it's extremely difficult to come up with a noise model that would affect all these components in the same way, such that the label would switch with high probability for all tasks.
Okay. Two more questions.
Yeah, hi. I would say one of the problems with neural networks is that it's basically a black box, so it's hard to understand what's going on inside. And you gave a nice example of looking at variants of filters to check if they make sense. Do you think that and there are lots of ways to visualize neural networks, but it's mainly done for illustrative purposes. Do you think that visualizations are in some way useful for kind of debugging of neural networks or not?
Absolutely they are. It is true that when we started out, we sort of built these models and they were kind of like black boxes. We knew that they work, but we didn't really know why. Over time, sort of the black box becomes more gray and transparent. People don't care about sort of local minima anymore because we've shown that it's not a problem because there are multiple local minima and they're all within an epsilon of a global minimum, so it's not a big deal. Visualizing as much about the network gives you intuition as to what's going on. If you have a bunch of redundant filters that you've learned, chances are you're not doing well. If you have a bunch of empty filters, that also means you're not doing well. From the perspective of generalization and domain adaptation, there's been sort of a lot of progress made in the last few years. Remember, this whole business is only 5 years old. People have been working, including myself, on computer vision for 40, 50 years, and they've never been able to achieve sort of the same quality of results. So it's still in its very early days, but the more you visualize, the more intuition you gain about what's going on.
Next question.
Thanks a lot for inspiring. And do you think mixed reality tasks going to be completed in 2020?
I don't know what's complete. I know that there will be devices out there by then that you'll be able to experience mixed reality in. But it's such a new sort of way of computing that it's not clear where the boundary is. Will it be able to replace your phone by 2020? Probably. Will it be able to replace your TV? Absolutely. Will it be able to completely replace your laptop? I'm not sure.
More questions? Okay.
Thank you for the presentation. It was impressive. I have a question. Let's assume that there are two face recognition systems. One is the conventional feature-based system, and the other is a deep learning-based system. These are well designed with today's technology, and they are used in a city by the cameras spread all over the place. And every citizen has his or her picture in a database. And let's assume there is a person who is a computer vision expert and also at the same time good at makeup. And this guy is at the same time is a criminal. But he doesn't have any a priori knowledge about the system design, which features are used or which training sets are utilized. Which system would be easier for him to cheat?
So the sort of the implicit attraction of learning-based systems is that they can always improve. The downside of feature-engineered models is that they get to a certain baseline with some amount of work, and to make them better is virtually impossible. That's why progress in computer vision and face recognition, for that matter, has been so slow, because you have to come up with something really new to input into the system by hand for it to sort of improve in performance. So I would say that it really depends on the systems, on which one is sort of more robust and which one is easier to cheat. But I guarantee you that over time, so maybe the first time it would be able to cheat it easy, but as it tries to do it more and more and more, the deep nets or the learned systems are much, much more robust because they can adapt to what's going on. So they get better. With every cheat that they observe, they get better. Other systems don't.
Another question? Okay.
Hey, thank you. So, at the end you said that there will be the part when machines teach themselves. Can you, let us know about your ideas, how it could work?
So this is basically an example of sort of unsupervised learning. So nowadays you see there are a few examples, and GANs being sort of the most shiny of them. But imagine a scenario where you go to a machine and you say, my child is going to sleep and I have to tell him a bedtime story, but I completely ran out of stories and I'm just going crazy. And then the computer says, well, what does your child like? And then you name like a bunch of different things that the kid likes, and then the machine then goes and just creates a story. Because it has read every single story in the world that's ever been written, and then it can synthesize something new, assuming that it has some creativity notion, and the loss function allows you to prevent saying things that don't make sense, and eventually it creates a story and tells it to the kid. So that's an example.
Yeah, I got it. It's like how it will be. It will look like for humans, how it will look like technically.
So technically, it's some generative model that has been trained on examples in the world, and it knows what the composition is. So then you say, I want you to reverse the process and map the composition into the real world, modulo that it doesn't repeat anything that it has ever seen.
Okay, we have. Okay, this is the last question, guys. Sorry, we are late, but yeah.
Thank you. I have sort of a meta question. Recently, there were some legislative effort to sort of ban deep learning. So basically, in EU,
in Russia.
No, in EU, somebody proposed that software authors have to explain what's going on under the hood. That's one thing to do, and another is that deep learning systems, they can learn biases as people do, and it may lead to this racial biases or anything like that. So this is a question of ethics. What do you think about this setting?
I think you have to be careful about how these results are interpreted and what they're used for. But this is evolution, and fighting evolution is kind of stupid. So.
Okay, last question. I will take last question, and yeah.
What's your opinion about adding temporal dimension for convolutional network? For example, for taking in account some sequence of frames for motion, for example, detection, and structure for motion, etc. So it's not mentioned into your.
So I actually mentioned this in the talk, but I went over it briefly. You're certainly right that the world is dynamic, and these models have to be dynamic as well. So there's a number of tasks, both in vision and in speech and machine translation, that use recurrent networks. So these are convolutional networks that are connected in time. The most sort of practical and useful one is called an LSTM model, a long short-term memory model that was invented a while ago. However, I can analytically prove to you that any recurrent network can be written as a feed-forward model. It's just a lot simpler to train a recurrent model versus a very deep feed-forward model with auxiliary inputs, but analytically these things are the same.
Andrew, thank you very much for your talk.
Thank you.